Here we see simple harmonic motion in greater detail. The wheel at the left of the screen represents the Ferris wheel seen previously, and the filled dot on the wheel represents the passenger who was holding the flashlight. We will define the point on the wheel, marked as 0 degrees, as the starting or equilibrium position. When the wheel is rotated counterclockwise, the filled dot moves around the circumference of a circle through various degrees of rotation, marked in 45-degree intervals. At the end of one complete revolution of the wheel, the dot has moved through 360 degrees. At the right of the screen, we see the projection of simple harmonic motion, just as we saw previously with the Ferris wheel. This projection can be described as a displacement waveform because it reflects how the magnitude and direction of displacement of the filled dot vary as the dot moves through 360 degrees. The dashed line connects the filled dot on the wheel to an open dot on the displacement waveform at the right to enable us to see that the movement of the two dots is synchronized. The displacement waveform is marked in 45-degree intervals along the horizontal axis. Degrees on the horizontal axis for the displacement waveform at the right correspond exactly to degrees of rotation around the circumference of the circle at the left. At 0 degrees on the circle, the filled dot is at equilibrium, and the open dot on the waveform at the right shows 0 displacement. At 45 degrees of rotation on the circle, the 45-degree mark on the waveform at the right shows displacement upward. As the filled dot continues to move counterclockwise around the circle from 45 degrees to 90 degrees, it travels once again through 45 degrees. At the 90-degree mark, the height of the displacement waveform is at its maximum. This corresponds to the filled dot being at the highest point above the baseline. Even though 45 degrees lies halfway between 0 and 90 degrees, the amount of positive displacement at 45 degrees is not half of the displacement at 90 degrees. We will learn later that we actually achieve about 71% of maximum displacement between 0 and 45 degrees. Only 29% of maximum displacement is therefore accomplished as the dot moves from 45 degrees to 90 degrees. Between 90 degrees and 270 degrees, the filled dot on the wheel moves downward, and the open dot on the displacement waveform also moves downward from a maximum positive displacement at 90 degrees to a maximum negative displacement at 270 degrees. Finally, the filled dot on the wheel moves upward from 270 degrees to 360 degrees, shown in the illustration as 0 degrees, and the displacement waveform at the right returns to the reference baseline. Movement of the filled dot through 360 degrees constitutes one cycle of rotation. This is consistent with previous definitions of a cycle. Equilibrium corresponds to 0 degrees, to maximum displacement 90 degrees, back to equilibrium 180 degrees, to maximum displacement in the opposite direction 270 degrees, and finally back to equilibrium 360 or 0 degrees to start a new cycle. Thus we have seen that the displacement waveform at the right of the screen shows the magnitude and direction of displacement on the vertical axis as a function of degrees of rotation on the horizontal axis. The horizontal axis also can be labeled in units of time. Suppose, for example, that the filled dot on the wheel completes 100 cycles of rotation per second. That means its frequency, the number of cycles per second, is 100 Hertz. Therefore, the period of rotation, the time required to complete just one cycle of rotation, is 1/100th of a second, or 10 milliseconds. If the frequency were increased from 100 to 200 Hertz, the period would decrease from 10 milliseconds to 5 milliseconds.